So 2 factors, full factorial design without replication. So obviously there is a chapter with replication coming up. So the outline is basically the same as before: how to compute the effects, how to find the errors, how to do the ANOVA table, visual test, confidence intervals, and here we are going to use multiplicative models and missing observations. Those are the 2 complications. So 2-factor full factorial design. So this is basically, we are not saying 2 raised to k, we are saying you have just 2 factors but any number of parameters. You could have 3 levels for one and 5 levels for the other. So 3 times 5. 3 raised to 1 times 5 raised to 1. Right? And so many of the exercises that we did before, just like we also compared that in the question answer session, we had a workload and code size study. That one would be a 2-factor study because the workload is a factor and the processor is a factor. So we are assuming that the factors are categorical, and if they are not, then you can use a regression model. And then, so basically, let's continue with that. The model is now, and this is the most important thing, is that the model is Yij is equal to mu plus alpha j plus beta I plus Eij. Now, let's see. Basically, we are putting Y as a matrix where J and I basically columns and rows, and then so the overall response is mu, and for every value of alpha you have alpha 1, alpha 2, alpha 3, whatever number of levels you have, and for beta you have similarly the levels. Actually, example will make it much more clearer than this expression. So let's see. Before I go to the example, let's just finish some of the notation. We already did the notation of y var. Y var dot j means we are going to average along the I-axis. So we will add all the y's for the same value of j, for one fixed value of j. And therefore, when you add up, the j is fixed, alpha j will remain, and but betas will change, so you will have 1 upon b and 1 upon b here. We assume this is 0 and we assume this is 0, and therefore all you get is first 2 terms. Why the second term, third term is 0? Because this is our assumption in the model. In the model we assume that all the effects will add up to 0, and all these effects will add up to 0, so that whatever is, if they don't, basically is the common thing, will go into the mu. So mu takes care of anything that is common. Alright? Anything that is different goes into alpha j and beta I, and therefore these things will add up to 0. Errors obviously add up to 0. So this is 0, this is 0, and so if you take the mean along this I-axis, you will get alpha j. Similarly, if you take the mean along the j-axis, you get beta I. If you take the mean along both of them, you get mu. And therefore, you can calculate alpha j, beta I, and mu together. Now, so example will make it clear. Now, so we have this example where there are 2 cache, 1 cache, no cache. These are the workloads, and this is the performance. Alright, it doesn't say what performance it is, so let's just go along with that. We'll see what it is. But anyway, these are the numbers for the performance. 5. This factor has 5 levels, and this factor has 3 levels. 3 by 5. So we do a row sum and row mean and row effect. Basically, so we add up these things. This is the sum of these 3 numbers, this is the sum of these 3 numbers, and so on and so forth. Similarly, we add up the columns. Alright? And then we add up the overall thing, which is 1083, sum of all of them, and divide by 15, we get 72. So now this is mu plus the effect, and therefore we subtract the 72 from here, and we get the effect. So when you subtract 72 from 71, you get minus 0.5. Similarly, when you subtract it from 8172.2, you get 8.8, and so on and so forth. So this is the effect of this workload. This is the effect of this workload, and so on. And you can see that these effects add up to 0. Similarly, we do the column wise. We get the column mean. And how do we get the column mean? We do the column sum and then divide this number by what? By 5. Right? So we get 51, 52, 51, 33. Subtract 72 and we get these effects. Subtract from 51, 72, you get minus 21. So these are the effects of the caches, and they add up to 0 again as we defined. So how do you interpret this result? This result, now this was actually a time, it says time. So this result says that the average workload on an average processor requires 72 milliseconds. With 2 caches, you save 21 milliseconds. With 1 cache, you save 20 milliseconds. And if you have no cache, then your time will be more, like 14 1 second more than the mean. Yeah.
So 2 caches, 1 cache, and no cache are the levels of the factorial cache?
Those are the three levels, yeah.
Okay.
Yeah. Yeah. And the workload is also a factor here, and it has 5 levels. Now, we are really not interested in finding out, which workload has what. So it is really, but it is an important factor what we are interested in this line here. And but here what we are interested to see when we do the overall model is that somehow our workloads are not so different that basically they explain 90% of the variation then we didn't do our workload right. Okay, because you really in your experiment you minimize the effect of the important thing that you really wanted to study just by design.
Why did that happen?
Right now it didn't happen. I'm not saying that it happened, but if it happens, suppose you take 2 workloads which are very, very different, alright, then it will come out that the workload caused 90% of the variation and the processors make very little. And then you will conclude that basically processors are not important, it's the workload, right? So if you want to see the difference between the processors, then maybe you have to change the design, you have to change those levels of the workload. Alright, so everybody can do this matrix thing. This is not really a matrix thing that much, but you have to do row mean and the column mean. And then you have to do the interpretation. So let's see, where did we go? Okay, all right. So once you have done the page up. Okay, so this one you can do. The next one is interpretation. That 2 cache minus 1 cache is only 1 millisecond difference, right? So that doesn't look like very important. But you will want to see if it is significant. If you have a statistical bent, you will want to see whether this is significant difference, right? And so we will basically have to see how to do the confidence interval. And this is a contrast because the coefficient will add up to 0. So this, you can calculate the confidence interval for this contrast. This is similarly a contrast, and it is clear that the cache make a lot of difference. Between 1 cache and no cache, the total difference is 61 milliseconds, which is almost like the mean, 72. Right? So caches do make a very important difference, and obviously we'll see whether this is significant or not. And the workloads also affect, and you can talk about the workloads very similar, that one workload takes 8 milliseconds than the average, higher than the average, other takes 0.5 milliseconds less than the average, and so on.
Question.
Yeah.
Can you tell me why with the contrast you
Oh, because the signs were different. No, it was not add, it is subtraction here. It was 41.4 minus 20.2. Right? It was a minus sign which I didn't show. That two minuses become a plus.
So are you saying about the workload? It doesn't seem like a big difference.
No, in this case it is not. No. Please. I didn't say that this in particular example it is a big difference. In some example you might get a big difference.
Okay.
If you get that, then you know. And that example actually is that case that you had. Remember that case you brought up that the numbers were 200, ratio was 200? Yeah, in that case, when you do the same analysis here, which I think is probably either in homework or something else, okay? If you do that analysis now, in this chapter, you will find that the workloads, are overwhelming. All right. So now we have to go to the confidence interval. How do we do the confidence interval? We calculate the errors. We calculate the sum of the errors, and once we calculate the sum of the squared errors, then all we have to do is so basically for each one we do the prediction. Now, but the question is, what is the prediction? So the predicted value is simply mu I plus alpha I plus beta I, right? Alpha j plus beta I, which is simply this plus this effect plus this effect. So instead of 54, your prediction would be 72 minus 0.5 minus 21.2, right? That would be your prediction, and when you subtract that from 54, you get the error. Alright, so the prediction is the column effect plus the row effect plus the mean, that for that cell. For this cell, the prediction would be mean plus the column effect plus the row effect. Sorry, I'm just saying, plus the row effect and the column effect. So for every cell, you have the prediction and you have the error. Right? When you add up, so these are the errors you will get in those 15 cells. Now you add them up, you get the sum of squared errors. And basically, as before, the sum of squared errors will add up to sum of squared errors due to A plus sum of squared errors due to B plus SSA, SSB plus SSE will be equal to SST. What is SST? SST is simply the thing that you will do for the variance of y, which means the total sum of squares of y minus y bar squares, right? So SSY minus y, this one will give you the total variation, 13,000. Out of that, 12,000 is explained by A, 3,000 by B, and that means that 95% is explained by the caches, which is good, and 2.3% is explained by the workloads, and 1.8% is error, which is even good because errors are very little. Yeah.
I'm not sure I understand what two differences of just use the metric technique. There are in 2 to k factorial design when k is 1. What is the difference between two factors?
Okay, if it is 2 factor, we will get the same answer.
Okay.
There is no difference. If you have 2 levels, you think if you have 2 levels, whether you do it by this method or previous method, you will get exactly the same answer.
Because the two levels in the 2 to k, yeah.
Yeah.
Okay.
Right? This is now more than 2 levels. And so we can do the F test as before. We have degrees of freedom. A times B. A is the number of levels of first factor. B is the number of levels of the second factor. So this is like 15. 3 times 5, 15. And out of that, the by bar uses up 1. SSA uses up A minus 1 degrees of freedom. B uses B minus 1 degrees of freedom, because that is how many parameters we have estimated. This is how many parameters we have estimated. This is how many parameters we have estimated. And so the errors are left with this many. This is just comes from the subtraction. and therefore divide the sum of squares by the degrees of freedom to get the mean squares. Mean squares of A is that, mean squares of B is that, mean squares of error is that. Simply dividing, right? And then you take the ratios to get the F test. MSA upon MSE will give you one F value whose numerator has A minus 1 degrees of freedom. MSA has A minus 1 degrees of freedom. The denominator has A minus 1 times B minus 1 degrees of freedom. And similarly, MSB upon MSE will be another F factor, and you will see if it is significant, right? So you make a table like this, which we are going to make in a minute for an example, but basically it's very similar to what we have been doing so far, except that now there are two factors, A and B. So there are two F values, and then this MSE can also be used to calculate the squared standard deviation of errors. So so basically here is the example that we were doing for the cases. The total sum of squares was 91,000. Out of that, if you just took 72, remember that y bar dot dot was 72 point something. That was the overall mean. If you square that and multiply by 15, you will get this number, 78,000. And then subtract that and you get 13,000 for the total variation. The caches contribute 12,857.2. Now you should know how to calculate that number. That number here, SSA is simply B times alpha j squares. Okay, so you have the alpha values, which are the column effects. Square them up, add them up, and multiply by the number of rows. Similarly, SSB you compute from the effects and the A value. So if you put those, you get these two, and then the errors, you can check out that they add up to exactly that value, because errors can also be calculated by calculating the errors and summing them up. So all of that is corrected, and then you can just do the ratios to find out that this is 95% and this is 2.3% of that number, and so on and so forth. So now you can see the importance. Then you divide by the degrees of freedom. This is the degrees of freedom, is A times B minus 1. So that are 15 minus 1. And so forth. Errors have A minus 1 times B minus 1. So A minus 1 is 2, B minus 1 is 4. Errors have 8 degrees of freedom. They will add up again. And then you divide and you get the mean squared errors. And then you divide MSA by MSE. So 64 divided by 29, you get 217. 77 divided by 29, you get 2.6. You go to the F table, 31, 3.1. How do you look up 3.1? You have to look up for 2 degrees of freedom and 8 degrees of freedom. Numerator is 2, denominator is 8, and whatever confidence interval we thought about here, 0.9 or something like that. So you will get this from the table, and this says this is higher, this says this is lower. So the cases is significant, workloads are insignificant. So let's go back to here. The workloads are not important and not significant, we don't care. Alright. Now, since we have SE, we can do the confidence intervals now. And before the confidence, the tests are very similar, like just like before. We check the normality, and we check standard deviation is constant, and we also check that the ranges of the errors are very low. We could do this test like we talked about here, because that's also an assumption here on the board. We talked about plotting errors as a function of the levels, and I think this will pass. Anyway, this is the variance formula, and once you know the variance, you can just use the confidence interval using t values. So there is not much new here except some formulas. So standard deviation of errors is given, standard deviation of mu you can find out, standard deviation of alpha j you can find out, and beta j you can find out using the formulas. Once you know, you can put the confidence intervals and you can see if something is 0. So nothing is 0, nothing is 0, nothing is 0, nothing is 0. So all the three cases are good. This is a good news actually, although this is an example and so means nothing. The workloads are all insignificant except for the Pico, which is different. So it turns out that that workload was out of ordinary, but not that is important to us anyway. Now if you want to do the contrast, so this is a contrast. If you do 2 cache minus 1 cache, there is not significant difference. So remember, the 2 cache minus 1 cache has 1 millisecond different. So really what it is saying is that if you didn't want to put money, don't worry about 2 caches, 1 cache is good enough. Okay? Between 1 cache and no cache, there is a significant difference. This is not 0. And between 2 cache and no cache, there is a significant difference. This is not 0. So you really should put money in the cache if you can. Again, this depends upon the financial decision as to how much it is cost. Alright, so the last thing is multiplicative model, is that we assumed additivity here. But this may not be the case. Alright, just like we know in the execution workload execution. If it is not, then you will need to find out what kind of transformation we use. And this whole chapter on transformation, which we did in chapter 15, comes back here. Start with the log, multiplicative, non-log, plot the graphs, find out G, H, everything applies. Alright, so that is, I'm not going to repeat that, but that is what basically applies to all the models. Then missing observations. So if you have some observations missing, so for example, the matrix that we had 3 by 5, it will not be 15, it could be some numbers are missing. Then you have to be careful. One is that you basically divide each sum by the number of terms that it uses, and you can continue that. The main thing is that the standard deviation formulas will have to be adjusted. Alright, and I wouldn't select the alternative, so let's just not worry about that. And so maybe I was going to say that let me give you an example of missing observation, and it's very easy. I'm just going to show it to you right here. Let's say this number 120 is missing. What will you do is, you will add up these two numbers, will come out, the sum will come out 86. You will divide by 2 to get the mean. Right, will be 43, and then you will subtract and you will get the effect. Right. Similarly, when you add this number here, you will have some number which you will divide by 4 to get the mean. Right, and then you will subtract from this. Now to get this number, you will add up all these, and if this 120 is missing, you will have 14 numbers, so divide this sum by 14. Everybody gets it, how to use that? The main thing is that these formulas that I have given you for confidence interval, they are different for missing observations. They are a little bit more complicated than I want to do here. Okay? Because these assume full observations. And so you will have to look it up. Alright, that brings us to the end of this chapter. Two-factor design without replication. The model is simply the mean plus the effect of the first factor plus the effect of the second factor plus the errors. The effects are computed so that they add up to 0, and the effect can be computed from the means along the 2 dimensions. The standard is, sum of squares add up. There are 2 important sum of squares, SSA and SSB. So you calculate the mean squares from the degrees of freedom, and then you calculate the 2 F values. And now the 2 F values may be contradictory, just like we found out that in our model right now, we found out that the caches are significant, but the workloads are not significant, and so that's okay, because that's what we really wanted to anyway to begin with, is that we are interested in the caches and not in the workloads. If it was that workload was, so I mean basically, here is the thing, then you have to go back to this and see if it is important and significant and so on and so forth. It turns out the workload were both not significant, not important. So we go ignore the parameter and move on. Oh, standard deviation is there, contrasts are there, confidence intervals using t-values, assumptions are same thing, IID, zero mean, and constant. The visual tests are same. And I will somehow emphasize this part. I think I missed this to show even an example of this. I will show at least an example in the next time. So there is a homework, and it is very simple, 3 by 5. So it can't be any better, except that this will require, now I am going to give you the solution here, this will not pass the test. This is execution time. And you know about the processor and the workload, execution times multiply. Right? So this will not pass the test. Then you will have to do a log. Log will pass the test. Right? And you can see that also by the ratios. You are adding up 39 to 0.019. The ratio is just too large. So you don't want to add up these numbers like that. Alright, so when you see the thing like this, then you will find out. So this is, I think this is first saying you do it, and then what would you do as a good model? And I think the answer clearly is that you will have to do multiplicative log.